In these sessions, we hear about exciting innovations ranging from AI-assisted disease modeling and emergency preparedness to surveillance among marginalized patients and even novel multi-disease monitoring approaches. To guide us through this session, I am pleased to introduce our moderator, Ibu Annisa Rahmanti, Doctor of Philosophy from Universitas Gadjah Mada. Ibu Annisa is a lecturer and researcher at the Department of Health Policy and Management, Faculty of Medicine, Public Health and Nursing, Universitas Gadjah Mada, Indonesia. She completed a postdoctoral fellowship at Middle University London as a British Council Women in STEM Fellow. Her research interests scoping artificial intelligence, natural language processing, machine learning, and nutrition informatics. She is also the second winner of TMU Holt Prize and 2021 a Holt Prize Impact Summit Regional Finalist in 2020. Without further ado, ladies and gentlemen, please welcome Ibu Annisa Ristya Rahmanti, Dr. Philosophy. Ibu Annisa.
Thank you, Rima, for the kind introductions. Good afternoon, everyone, and welcome back from the lunch break. You are feeling recharged and ready for session 3 on technology and data analytics in mosquito-borne disease surveillance, as introduced by Rima. I'm Annisa from Universitas Gadjah Mada, and I'll be your moderator for this session. It's really wonderful to see such a broad interest from more than 100 participants joining us here in Zoom. We also have 3 distinguished speaker lineup today, and each speaker will have 15 minutes for their talk. And also, I think the organizer will also provide a countdown timer to help the speaker keep track. And then I will also gently remind you the time is up. And after all the 3 presentations, we will have a Q&A session, just like the previous talk. So please prepare questions in advance. Before we begin, maybe I would like to ask the audience, how is your team currently using technology in mosquito surveillance? I think that you have to hold your thought from our speakers. I would like to invite our first speakers, Dr. Watsiq Maula, or I usually call him Dr. Wawa. Maybe the organizer can help me share the screen. Yeah. Wawa is a lecturer at the Department of Biostatistics, Epidemiology, and Population Health, Universitas Gadjah Mada, and he's also a researcher in the Artificial Intelligence for Pandemic and Epidemic Preparedness and the Center for Tropical Medicine. And his expertise span from epidemiology, biostatistics, and AI-assisted disease modeling. And Dr. Wawa will present on AI-assisted disease modeling and emergency preparedness. Welcome, Dr. Wawa.
Yeah, good afternoon, Annisa. Thank you for the opportunity for the committee of Mosquito Day webinar. So let me share my screen. Okay, is it visible?
Yes.
Okay. Yeah. Let me introduce myself first. So I'm Ahmad Watsiq Maula. I'm from Universitas Gadjah Mada from Department of Biostatistics, Epidemiology, and Population Health. Today I will present about AI-assisted disease modeling and emergency preparedness. I hope I have a very concise presentation because it's only 15 minutes. Even I'm using help from AI, is still pretty hard to develop the slide for 15 minutes. Okay. So this is a little bit about my background. As I mentioned before, I'm a faculty and also researcher. Mostly I work with Center for Tropical Medicine in Universitas Gadjah Mada and also Pediatric Research Office. Right now I'm working in one of project called AI for pandemic and epidemic preparedness. And also I involved in another project is also related to the pandemic preparedness. It's wastewater surveillance for pandemic preparedness. So both project is related to the pandemic preparedness. The one is with enhancing the AI. The another one is using alternative surveillance using wastewater. So for this topic, so I will present about the disease modeling issue and AI for the disease modeling, issue in the disease modeling, current AI implementation in disease modeling, and also AI in disease modeling with one of our project, explain dengue, which included in AI for project. Okay, so what is disease modeling? So like we know, we have a lot of real world problem. For the example of this presentation, I'm using a car with a very complex system. It has engine, it has electricity, it has interior, exterior, and suspension, transmission, and so on. And if we want to explain about the complex system of the car, sometimes we create a simple version of the car. So, for example, this one, we create a car from the cardboard to simplify our understanding about car. So basically, for the modeling, is it a process of simplification of system to understand complex real world problem. So we all of us who work in research area always using this concept, the modeling concept. We cannot capture all of the complex real world situation. We always try to thinking in a simple way. So we try to model the real world problem into the small scale or the concise version. So that's what we call modeling. And during we develop the model, sometimes we miss some part of the real world complexity, and we only capture part that we can explain or we can capture during our research or maybe in our thinking. So basically for the disease modeling, we can use either statistical model or mechanistic or mathematical model. In statistical model, we frequently use it. So for the statistical model, we rely on observed data. So basically, we cannot do the statistical model if we don't have a good data. We don't have any source of data. It will be impossible to do the statistical model. So that will be the problem of the statistical model. While the mechanistic or mathematical model, it's more like rely on theory, assumption, and also even we don't have a very good data, we can still develop the mathematical model. As you can see here, this is a very famous model from Ross McDonald to explain the mechanism of mosquito-borne disease. So basically, we can split the compartment disease in human and also the factor. So by using this mechanistic model, we can explain the transmission of the disease and the dynamic of the infection in the population. And for the mechanistic model, sometimes we don't need very good data, but sometimes we need some previous knowledge about some assumption to fill out the parameter. For example, the transmission rate of the disease, and sometimes we need like the rate of the progression of latent phase to infection, and sometimes we also need information related to the recovery rate and so on. Sometimes we can use assumption, sometimes we can use simulation, but it will be very good if we can use real world data or we can use observed data to fill in the parameter. And for the statistical, maybe you ever use like linear regression, logistic regression, and even right now we use a lot of machine learning method. All of that is rely on statistical method. And for example, here in dengue, we know that the climate is very related to dengue, like the increase in temperature, it will also increase the dengue notification. So that's two model that you can use to explain or maybe to infer a situation about the disease. Okay, so for the disease modeling, there is a issue that will become if we try to develop the model. For example, for statistical model, as I mentioned before, we need very good data, but sometimes the data is have an issue like data scarcity and quality issue. Like in Indonesia, like we know sometimes if we using the surveillance data, sometimes we have a problem on the sampling representativeness, like in the mathematical model, we also have that problem. Sometimes we want to input some value on the parameter. We don't have the data, so we need to use the assumption. So for the data scarcity and quality issue, it will impact the statistical model really bad. So we need to ensure that we have a good data quality if we want to develop the statistical model. And then computational complexity, as we know, by the growing of the technology, the analysis method is become very complex, and it's very computational intensive and need a lot of resource on that. And for the mechanistic model or mathematical model, for example, the Ross-McDonald model, since we need to input a lot of parameter in the model, for example, the transmission rate, and then also the bite rate from vector to human, and so on. Sometimes the parameterization and calibration is very difficult. There is a lot of method that we can use to put value into each parameter. And the traditional one, we can use like a brute force method. Like we use a set of parameter, the range of parameter, and we try to simulate manually, but that is very resource intensive. It needs a lot of time, and also computationally it's also need a very high resource. And for the time, it's very time consuming. And forecasting dynamic factors also become a problem. For the forecasting, it's also rely on very good data. And sometimes if we want to forecast, the extrinsic factor is very impactful in our forecasting. I will have example on COVID-19 after this. And the next one is early detection delays. As we know right now, we still a lack of real-time data. So if we want to do the early detection using the disease modeling, it's still very hard. For example, during the COVID-19, we have a lot of data related to the mobility of individual or mobility in the population, but right now it's very limited. So if we want to use the early detection using the data, it could cause a delay. And also, especially in Indonesia, the access to some data is very limited. So it will become really hard if we're using alternative data to develop some early detection modeling. So we need to have a good alternative method to method, or maybe a data source to develop the early detection modeling. For today's presentation, I will focus on two things here. The first one is data scarcity and quality issue, and also parameterization and calibration. So for data scarcity and quality issue, like we know during the COVID-19, there's a lot of researchers, a lot of academicians develop a model to predict maybe the number of cases and incidence of COVID-19. Maybe they also try to predict the needs of ICU beds, but all of that model is fail. Why it can happen? Because the first one, we have a poor data input, we have a wrong assumption, we have poor evidence on intervention, and selective reporting. So all of that stuff is causing a bad data quality. For example, during the first phase of COVID-19, to diagnose the patient, the gold standard is we don't have the PCR, but we using the antibody test to check if we can define the individual has COVID-19 or not. But by the progression of the COVID-19, it's changing. So the data quality become issue here, because at the beginning of the COVID-19, we have definition, and during this progression, we change the definition. So the data quality become problem. And if you remember, during COVID-19 at the early phase, many people develop model, so they still don't have enough data to infer, to forecast, to develop the model. So when they try to predict or try to forecast the number of COVID, the needs of ICU beds, it's wrong. Like we can see here, the prediction is the ICU beds will be increased and then decrease, but in reality, it's steady at some level. So that's why data quality will impact our models really hard. So as we can see here, for the modeling, it will be better if we not only using single data source. We need to integrate a complementary data set, so it could decrease the data scarcity and also improve the quality of the data, especially for the infectious disease modeling. So instead of using only single data, we need to combine all of the data, and that's also possible using the AI technology right now. And for the example of the explain dengue that I will present for this, it's using a lot of data to predict the dengue. And the next one is parameterization and calibration difficulties. Like I mentioned before, by using the grid search and like square error, sometimes it need a very it's time consuming and computationally intensive. And right now we have some AI assisted for parameterization. For example, surrogate modeling. It makes parameterization faster, and mostly it's using deep neural network. However, we can also using more simple machine learning method like SVM, or we can use random forest and so on. But right now is the deep neural network or neural network is most frequently used to surrogate modeling. So basically for the surrogate modeling, instead of simulate every single parameter, we only use important parameter and we try to predict another parameter. So it will be faster, and it will also give a good final fit model instead of using the grid search. So by using the DNN, it will be faster for parameterization, and also it will be give us a best fit parameter for the model. However, for the DNN, as we know, sometimes it's like a black box. We don't know what happened inside the process of deep neural network. However, it's still widely used to get a best parameter for the modeling. So
Dr.
this
Maula,
is
sorry, but the time is up. If you could kindly wrap up the key
okay.
point in 1 minute, please.
Okay, so yeah, so basically for the AI assisted in disease modeling, it's happening right now. So we can combine the traditional method like mathematical model or statistical model, and we add AI on it. So for example, here we have the explain dengue. Basically, use graph neural network. We're using a lot of data, climate, environment, spatial, and also eWorks data for the detection. And by using the AI, we can get a very good prediction. And since it's using many data source, it's also consider every single aspect of dengue to give us incidence prediction. And also you can read many more AI use in dengue also, like using Google Street View and also satellite imagery to detect where the mosquito breeding site will occur. So yeah, that's for me related to the AI assisted modeling and also for the emergency preparedness. So basically, AI is very helpful to helping develop your model, and also AI has a lot of potential for disease preparedness. Thank you, Annisa.
Thank you, Ms. Maula, for showing us how AI can move from mathematical modeling and also algorithm to real-world preparedness using like disease outbreak. And Dr. Maula, please stay with us. We'll just take a short pause before inviting you for the Q&A. Now let's move from predictive modeling to understanding the population on the ground. Would like to invite our second speaker, Dr. Lai Yan. I hope I'm pronouncing your name correctly, Dr. Lee. Dr. Lee is a senior lecturer at the Tropical Infectious Disease Research and Education Center in Malaya, Malaysia, and she's also served as the expert committee member uh, in the vaccine development under Malaysia's Ministry of Science and Technology. And she will share insight into surveillance of mosquito-borne disease among marginalized population in Malaysia. Please welcome Dr. Lee.
Thank you very much. Can you hear me?
Yes, we can hear you
All right,
clearly.
thank
Please
you.
go ahead.
So, good afternoon, everyone. Thank you very much to the organizing committee as well as the fellow representative speakers from Malaysia for accepting this invitation to speak at the webinar on this very momentous occasion. So, I just want to say thank you to the entire committee for being able to pull this off quite successfully. So today, I'm going to share with you our insights based on the surveillance of our mosquito-borne diseases among the forest fringe population that we have been working on for the past decade, but I took over one of the session. So this is only part of the data. So without further, let's start with my presentation. So the outline of today's presentation will be pretty typical scientific presentation on the background, the objectives, method, results, discussion, conclusions, future direction, as well as acknowledgements. So Malaysia, we are a developing tropical country, and then we are, of course, increasingly utilizing our land, and we are very much aware of the encroaching activities of humans to the forest. So this can lead to one of the issues that we have raised is that it is quite a concerning situation because it could lead to an emerging new normal virus. That's how we witness coronavirus is found. So the forest range area here in this study also covers the all palm tree plantations, and these are two areas we consider as rural areas. And we identified these forest fringe areas because it is considered as a blind spot in national surveillance, particularly for vector and vector-borne diseases. So just as the background, it has already been established that the proximity of residences and occupational lifestyle exposure to wildlife can lead to major emerging outbreaks such as SARS, MERS, and Ebola. Some of the examples here is the schematic representation of the Ebola cycle in the equatorial forest and how we can basically have enhanced monitoring to continually ensure that we are safe at the forefront of this forest. So because of our human foraging, hunting, and occupational activities, it does increase the risk of exposure and contact of the human to a wildlife reservoir for an infectious agent. And therefore, there is important need to recognize and enhance surveillance for this select agent is paramount for monitoring and preparedness of a major outbreak. So within Malaysia, we look into the population, which is the orang asli population. The community represents about 1% of the entire population and has managed to preserve their very unique lifestyle for many years throughout our development. They, over the years, also remain vulnerable to dengue, and they have showed geographical and demographic factors that basically contributed to their own increased risk of contracting dengue by living in these forest fringe areas as well. We added this site called the Palm Oil Plantation managed by FELDA, the Federal Development Authority, for that will be in charge of all the plantations in Malaysia. Basically, in a systematic review on surveillance of diseases among this forest fringe area, it is typically covering a lot of neglected tropical diseases, and dengue is just one of them, which has been highlighted in the recent publications in 2019. As we know that our activities for the development of the country has basically is due to the agricultural expansion. We have also heard it from many speakers before this that deforestation is a leading cause of concern. And basically our expansion of the industrial plantation did lead to drainage and conversions of large areas of peatland forests, resulting in a large release of carbon dioxide. So this land use changes does might impact the presence of vectors such as mosquitoes in these areas and how it transmits diseases. So a study on the forest conversion activities between 1988 to 2012 in Malaysia showed that accessibility of location to infrastructure has a future potential to be expanded to meet global demands. Basically, this shows that with the amount of the industrial oil plantations in the country, which is about 30%, most of them will continue to expand because of the existing infrastructure available at the site. So this goes to show that after a thorough analysis, there's only about 5% left of the forest that is considered perfectly suitable for a palm plantation because it has been used for agricultural expansion. Studies also showed that with low suitability, some of these forests are still converted to industrial palm, and this has been occurring since 2006. So there is probably not going to be a way to stop the agricultural expansion due to economic needs, but definitely has to be developed in a more sustainable manner. We have already known that these vector host spillover risk is basically prevalent for a lot of the viruses such as dengue, yellow fever, Zika, and is a threat of a global population, not only for humans, but also for animals such as the African swine fever virus. So the challenges for arbovirus and their major vectors such as mosquitoes and ticks is pretty much very high on the priority list right now globally. So in our efforts, surveillance gaps in hard-to-reach communities can provide an insight to expanded dengue surveillance in rural area and also look into the sentinel population for a potential of emerging viruses. So the objective of this study is basically to determine the seroprevalence of mosquito-borne disease, dengue, Zika, JEV, chikungunya in forest fringe areas and its risk factors. We also develop interventional tools in this community to improve dengue prevention behavior and evaluation of these interventional tools using KBP model, which is knowledge, beliefs, and practices. And we map the risk and burden of disease using land use, utilizing UAV mapping technology. So it is to generate insights that could guide the design of a comprehensive evidence-based surveillance system for mosquito-borne diseases in these forest fringe communities. The methodology is basically we selected the sites based on recommendations from the Jabatan, the Department of Rural Asli Development, as well as the Federal Land Development Authority, FELDA, and JACOA. And after obtaining the approvals, we basically go into the forest fringe areas to collect the blood samples, design the interventional calendar. When we designed the interventional calendar, it was based on our previous studies, identifying major information and gaps in knowledge, and also basically to be able to produce 12 key messages to give the participants to be reminded throughout the year on what are the important interventions to be practiced at their village. So The last part is that at the site, we also perform mosquito capture for further analysis on pathogen detection at the molecular level of hantavirus and alphavirus RNA. The serological samples that we obtain from the villages, we perform ELISA assay kits to detect IgG for dengue, Zika, chikungunya, and JEV. And lastly, at every single site, we also deploy a UAV to map the entire area to look into the land use survey. So these are some of the examples of the sampling sites that we went through. 9 villages for 3 states. 6 of them are orang asli villages. 3 are basically oil palm plantations. Requires a lot of coordination meetings with the head of village prior to entering the village. And after that, to share the results here, we collected 586 samples. Our target was 385 samples based on sample size calculation. And we found that dengue IgG prevalence was at 41.7% across all the marginalized, all the population living in the forest fringe area. Other than that, we also found the chikungunya IgG was found to be quite high, especially in the orang asli villages at 47% accordingly, quite similar to dengue. Based on our analysis, the predictors of this zero prevalence of dengue is also due to the level of education. Those who receive formal education had 50% less likely to be tested positive. And that the location was, that means the orang asli village seems to have a higher risk of dengue positive compared to the palm oil plantation. So at the sites, when we collected the mosquitoes at the various facilities, we found mostly are albopictus and some percentage of armigerous. So out of these samples, there were 3 samples that were detected positive based on our molecular detection of alpha viruses, and then only 1 that we were able to sequence to show the presence of chikungunya virus from RNA mosquito samples. With regards to the interventional calendar, what we published the results here. So in this particular sub-project, we have 609 paired responses, and then we wanted to look into how the dengue calendar could improve their impact of the knowledge, belief, and also practices. So from there, we showed that we found that primary and secondary level education showed high increments in prevention practice. This is post-analysis that we found that some of the community were still unable to read. So education does represent a very important aspect for all these interventional strategies that is worded to basically implement all these tools and make sure that they are able to apply them. And when we try to correlate the KPP results to serological association, so the high number of respondents said that they have never had dengue, but their IgG showed a different results because they were not aware that they already had dengue previously. And based on the knowledge intervention, we saw that yes, people with more knowledge on dengue does have a lower IgG positive, showing that there is some impact of knowledge about dengue prevention in the control of at the individual level for the IgG through prevalence. However, we also found that in the very specific questions, particularly for preventive measure, breeding of Aedes mosquito in-house can be prevented by covering water containers. A lot of them does answer it correctly, but they are also quite high in their IgG, showing that the lack of preventive practices despite knowing the practices itself. Overall, the health belief model on the KPP showed a lower IgG dengue positive for participant scorings higher than 1.82. over a total of 4 in the HBM model that we were studying, and that the dengue prevention practices, does show a lower IgG positive with a significant impact. There are a few key points that we notice here is that there are certain practices that we're not aware of, is that measures to prevent dengue patients for being bitten by mosquitoes, a lot of them say that they do not practice it or not aware of it. And then they also do not avoid intercourse with the spouse if he or she is infected with dengue fever. And most of them do not put dengue patients under bed nets. For the site analysis, we obtained the map from the UAV deployment, and then basically stitched the image together. And the land analysis was performed based on our digitalization of all the sites. So you can see here is a transition of how we move it into colorimetric method to basically profile the land use characterization of that particular site. What we notice put into the feature here would be the palm oil, the forest, the field or open areas, water bodies, and rubber plantation. When we put it into statistical analysis, the percentage of land use to the presence of IgG or positive or negative, we showed that there was a negative correlation that the higher the use of the land for palm oil, the lower the prevalence of IgG dengue positive. And basically, this is probably due to the more organized development of the palm oil plantation areas. So when we look into the map again, we simulated flooding areas from the sites to show that in the forested area, there were more pockets of potential flood areas that is near the residential area compared to the palm oil dominant site. And we're looking into ways to develop this into a association of the land use to IgG positive and negative risk for identification of areas. So as a discussion, yes, we noticed that seroprevalence of dengue are increasing among the orang asli population compared to previous. That dengue and chikungunya was found to be very much circulating in these communities. All three dengue, Zika, and chikungunya endemic to Malaysia. And there is that previously there was about 61% of seroprevalence in urban area compared to our findings of 41.6%. There were also reported cases of the convergence of the seroprevalence between urban and rural area, meaning that the urban area we probably would have the expectation that these forest fringe communities will continue to rise until it becomes the same as the urban area. Zika exposure among RSD and Felder settlers indicated higher seroprevalence among samples collected from 2 states, from Selangor and Pahang compared to Perak, and that out of all the samples, basically 7.5% of the samples were positive for all dengue, Zika, and chikungunya. We found that behavioral studies.
Sorry, Dr. Lee, the time is up. If you could kindly
sure.
Key point.
So behavioral studies and intervention is very important to increase the practices, but we have to basically look into ways to sustain all these practices, because it's not enough to do it just once, and you have to do it repeatedly for many years. So yes, and also the use of the mapping will be very important because it is tied to a more sustainable development strategy of the land use. So the future direction would be to basically recommend a continued enhanced surveillance in these forest range areas to link the land use to design of the risk zones and better control of the early detection warning system, and also to provide a more sustained effort for household level preventive practices. So in conclusion, the combination of serology, behavioral sciences, and geospatial tools can uncover a number of blind spots to help us design a better reach of intervention. So this project was funded by Mosquito-Borne and also our collaborators here. And special thanks to the field team who went into the jungle with me and also out of it all in one piece. Thank you very much.
Thank you, Dr. Lee. That was a powerful reminder that we can combine like innovative tool, like you mentioned, like drum mapping, some traditional approach, even with behavioral survey for population intervention. Okay, so now I would like to move to the third speaker, Dr. Henry Surendra. Dr. Henry is an associate professor and program coordinator of the Master of Public Health at Monash University in Indonesia. He has over 10 years experience in epidemiological research on infectious diseases with publication in a leading journal. So Andrew will present on novel multi-disease surveillance approach for mosquito-borne disease. Please welcome Dr. Henry.
Hi, good afternoon, everyone. Thank you very much for having me today in this really interesting webinar. So today I'm gonna be talking about the work that my team are currently doing in Indonesia in the scope of how we try to develop novel multi-disease surveillance for mosquito-borne diseases. As many of you have already heard from a lot of speakers today, that the control and surveillance of mosquito-borne diseases are really complex because um, you know, it consists of a lot of things from understanding of human mosquitoes and wildlife distribution, understanding how landscape composition, aquatic habitats, and also recently becoming hot topic is also understanding how land use changes and climate changes may affect the infectious uh, mosquito-borne diseases transmission dynamics in population. And as we already know that the current existing surveillance that we have in many settings, including Indonesia, are basically disease specific, which means it is unintegrated. So malaria program will do malaria surveillance, dengue will do their own surveillance. So that's for Zika, chikungunya, and others. And it normally requires a lot of resources in terms of human resources to do mosquito cages, for example, and to do case detection and case investigation. Um, the surveillance also often limited by the fact that we do have a limited diagnostic capacity in the field. It often also includes findings, population that are really hard to reach. For example, like miners, forest workers, like just the previous speaker also mentioned. And as we know that because of the nature of our existing system are basically passive case detection, meaning that we wait at health facilities for cases to come, and then we do report, and then we do then submit the report to the national level, which often result in lacking of good quality of data in terms of completeness and also the timeliness of data. Today, I'm going to be sharing about a case study that we are doing in Indonesia. So to overcome those challenges related to complexity of mosquito-borne disease surveillance, so we try to apply what we call as integrated multi-diseases surveillance in development areas of new capital city of Indonesia in East Kalimantan. So just a little bit of background story about why do we choose to do the study in that particular setting. As you know that Indonesia is planning to relocate the capital city from Jakarta, the urban settings, which basically free from malaria, to what we know as a hotspot of malaria and dengue in Ibu Kota Nusantara, located in Penajam Pasir Utara in East Kalimantan. According to our investigation on the existing surveillance data, we know that malaria remains prevalent. The data in 2024 suggested that there are still 558 cases of malaria, And we've also established that the particular setting where the new capital city is currently developed was named as the second highest, as a site with second highest incidence of dengue in Indonesia in 2024. And you can imagine this project, this large project, has already brought approximately 143,000 workers to the areas, and most of the workers are actually coming from areas outside of the endemic settings. This is just, the figure is just to illustrate how rapid and how massive the land use and the changes of the uh, areas where the IKN is currently developed. As you can see in here, the figure shows from the left side to the right side clearly shows how massive uh, the development is. Um, and as many previous studies suggested, these massive land use changes, massive movement of people, from non-endemic settings to endemic settings could lead to increase in a susceptible population. Number of susceptible population will be increased. And at the same time, it also likely increase number of imported malaria cases, for example, because some people came from endemic setting and then visited the new location of the capital city. And then it will also increase the number of people who we call as a mobile and migrant population, such as forest loggers, miners, and so on. Um, the development of the new capital city will also likely to create a more favorable factor habitats, because heavy machinery, the opening of new road can also lead to new breeding sites for mosquitoes, for example. And at the same time, the opening areas of the forest will also increase, a risk that is related to forest-related occupation. And at the same time, we also hypothesize that this development will likely to then, if not introduced, probably increase human and wildlife conflicts. And if we put this all together, we hypothesize that this could lead to resurgence of malaria and probably sustain, if not increase, in dengue transmission. It can also lead to emerging of zoonotic malaria, because our data also suggested that there was, in fact, a PCR confirmed P. nolsi cases in human in these settings. And then we also hypothesize that these changes may lead to increase in transmission of other mosquito-borne diseases like chikungunya, Zika, and GE, which we don't have data as for now. So the aim of the study in East Kalimantan is basically to evaluate the use of novel multiplex serological assay, link them with data collected from remote sensing data, and then combine them with an advanced statistical modeling to investigate mosquito-borne disease transmission dynamics in development area in Indonesia. We are collaborating with many collaborators and partners like from the WHO Indonesia, Ministry of Health, and also some colleagues, like Kimberly Fornis from the National University of Singapore, Dr. Inge, who also moderated the session before, and many other partners in local district health office. So when we try to identify our study sites, we do sort of data collecting data that will enable us to identify the forest loss in the study area, as you can see from the graph on my left side, and also analyze the case reported data on malaria, and then that enable us to then narrow down our study sites into a couple of areas which are still having ongoing malaria transmission. Zooming in into our study site, and then after we got more refined data, then we decided to do the study in a 8 villages, 5 villages in Ibu Kota Nusantara, which consists of 5 dengue hotspots, and 4 out of those 5 were also malaria endemic areas. So they share risk for both malaria and also dengue. And then we also selected 3 villages in the neighboring district. 2 malaria hotspots, 1 recently reporting human influenza infection, and then 1 is malaria-free area. So what we've done so far is we established a research team that consists of 6 lab technicians and 12 enumerators. And we also established 2 site labs that will enable us to perform sample collection, storage, and sample processing until we have them ready to be transferred to our lab at Oxford University Clinical Research Unit in Jakarta. We've done some engagement, stakeholders engagement to do site sensitization study, socialization, because we are going to enter to the village to do our sample collection. We've performed some training, including DCP and study procedure training. We evaluate our study flow in the field, and then we implemented our study by collecting blood samples, collecting complex epidemiological data, GPS location of the household, and so on. The progress of our works today, so it's still work in progress. Unfortunately, I will not be able to share any interesting result today. But basically, the project has been going really well. I think so far we've collected samples and complex data from 1,200 individuals from around 550 households. As you can see it here, we collected samples. We did some malaria RDT tests. We collect the bloods, we collect the household location, and so on. On top of that, in addition to do the serological survey, we also perform systematic literature review to understand environmental and also climate factors that may affect the risk of mosquito-borne diseases transmission in our study areas. And we also collected Earth observation data like climate data, land use cover, and so on. And we coupled them also with collecting existing surveillance data like number of malaria cases and number of dengue cases over time and over places. So then with the hope that we will be able to link those complex data to better understand the epidemiology of multiple mosquito-borne diseases in these study settings. In our previous work, we actually have done it where we link the use of novel multiplex serological assay, and then we link them with complex epidemiological data to investigate the transmission dynamic of malaria in one of the setting in Kulon Progo district in Yogyakarta. We analyzed the samples against around 25 different antigens for different malaria species. So what we are trying to do in this new project in IKN is that to utilize that machine that will enable us to have a data for up to, depending on the type of machine, but the machine that we have now in our lab will enable us to detect the antibody responses up to hundreds different antigens. Imagine if we have 100 different diseases, and then that means that we can have we can analyze the antibody responses up to 100 different diseases in using one single samples. And in our future analysis, what we are trying to do is, we want to develop this map for different type of mosquito-borne diseases. Like example that I took here from a paper published by colleagues at London School, Hygiene and Tropical Medicine, where they use different antigens of different diseases, and then they basically estimate the seroprevalence for each diseases across space. What do we expect from this project is basically the long-term impact that we are hoping from this project is that by doing this integrated multi-disease surveillance, we are hoping that we could strengthen the surveillance and elimination efforts, not only for single diseases, but also at the same time for multiple diseases like malaria, dengue, Zika, chikungunya, and GE, depending on what we found what we find later on in the field. So this project will also generate new knowledge and new information about the epidemiology, the risk factors, the spatial patterns, including environmental and also climate factors that are associated with increased risk of transmission for each diseases, and also at the same time for multiple diseases in case they happen to share similar risk factors. Um, Future directions. So after we do this project, we are hoping at the same time now we are trying to get more funding, basically to do a longitudinal study in the same area in East Kalimantan, where we want to try to integrate this integrated multi-disease serological surveillance into the existing surveillance system that are currently running in the setting. So basically what we want to do is to find out how to best design and how to best integrate the multi-disease surveillance to better inform disease control um, and elimination. So uh, these two screenshots that I put here is basically to illustrate that there are some initiative, for example, in here in Cambodia, where they try to integrate the use of multiplex serological assay into their national population-based survey to basically better understand the multiple diseases transmission dynamic and population level immunity for certain vaccine preventable diseases in the setting. And then if you see in my left side screen, there is a toolkit for integrated serosurveillance of communicable disease in the Americas. Basically, generated and published by the WHO, specifically for those programs in the Americas. So in the future, we would like to see this kind of implementation to be happening in Indonesia, because we think it's going to be really useful for our disease control and surveillance effort. Last one, I would like to thanks all the study team and also those village malaria workers, those primary healthcare workers that are being involved in our study. So this picture is taken in one of the malaria hotspot, which is really located in hard to reach area where we have to travel like 8 hours round trip using a four-wheel drive cars to be able to get to these settings to meet with what we call as hard to reach population and high risk group for malaria, because they are spending months living inside the forest to do their job as a forest worker. So finally, I'd like to acknowledge that this work is funded by Wellcome Trust through Moru Oktu Discovery Research Academy, and also supported by the National University of Singapore. Yeah, I think that's all from me. Looking forward for the discussion. Thank you.
Okay, thank you so much, Dr. Henry. A great way to run up the session from AI, the population survey to integrated system. Now, again, I would like to say thank you to all our three speakers for the insightful presentation. We are now moved to the Q&A session. I think we still have around 12 minutes for the Q&A session. For the first question, I will be reading the list of the questions displayed on the screen. The first question, I think, dedicated to Dr. Wawa. So please kindly share your experience in building an AI model to be used in disease prevention and management program in Indonesia, and what challenge did you face the most, and also the to overcome it? Yeah, please, maybe Dr. Wawa, if you could answer the question first.
Yeah. Thank you, Bu Helvi, for the question. So, based on our experience developing the prediction tool for dengue using the climate data and also another data source. The main challenge is the source of data. For example, for the climate data, we try to looking for data that have a very detailed level of observation, not in monthly average, but we try to find the data that has daily climate data. So we need to looking for that data that publicly available. So we found two sources of data for that purpose. The first one is open weather data. If you want to develop any prediction model using climate, you can use that one. And also NASA, they provide satellite derived climate data and it's also publicly available. So basically you can pinpoint the coordinate of the location and you can get like a precipitation, the temperature and so on from the data. So that will be the main challenge is data source if we want to develop such a model in Indonesia. And also another problem is when we discuss in team like the surveillance data is for dengue. In our explain dengue project, we only using data from EWARS from S.Gz because that's the only surveillance data that we have access to. But however, for the EWARS, it's like a syndromic surveillance, so it's not precisely for dengue. So that's also the limitation if you want to develop the model. So for the historical data itself from the surveillance, we also need that one in a good quality data for the surveillance. And it's really depend on the disease. For example, if you want to develop for TB, we already have SITB in Indonesia, and they have a lot of data and very detailed. But for the another disease, maybe that not quite common in Indonesia, it will be really difficult. But for the alternative data source like the climate and then vegetation index, we also get that one from NASA. That's publicly available. So yeah, you can contact our team if you want to know how to access those data and want to develop some prediction model or forecasting model for any kind of disease.
Yeah, thank you, Dr. Wawa. So so second questions from Healthy to Dr. Lee. She asking about what is your suggestion to substitute drone mapping with image from Google Earth or Google Map to recreate the study in another setting? And is there any health center with survey population in your area of study? And there are background status of mosquito-borne infection of this particular community and maybe the outcome of your study.
Okay, thank you very much for the question. Very, very good question. So for the first question is that any other alternative to replace images? Yes, you can use Google Images, but they are pretty low resolution, which is why they also don't provide you the topography. That means like the high and lows. If you're looking to simulate flood, it's not enough, but you can try to look at your national authority, because there are some in Malaysia we do have an authority that basically sells the map from Malaysia in very selected areas. So you can try to buy those map from them and see whether they have those right resolution or not. So that is for question number 1. And the second question is that whether there is a hospital or center. Yes, there is one specific health center for the indigenous population. It is quite specialized for them. And they do have some level of mosquito surveillance, but mostly it was done in publications. We only search for publications in the domains where it's accessible to all. So perhaps those data were not available to most, especially in their own internal circulation. What was the third question? Can I get back to? Sorry, you're muted.
Sorry. So related to the outcome of your study?
All right, so the outcome of the study is that first, with regards to the seroprevalence, we do find a silent circulation of chikungunya at the time where we were doing the investigation. And the following year, we do observe chikungunya outbreak within the states that we found it as well. And the second part was that there is a great demand with regards to developing the indigenous population, is that they have quite a number of issues to handle, to work on, including clean water and education. So it seems that interventional tools for dengue is something that we need to devise other ways so that it can be integrated into their homes or their lifestyle. So either that you're preparing nets for them and just have them to use it rather than to come in through an educational strategy. Last but not least is that the whole aim of the GIS mapping or the geospatial mapping was basically to tie up the land use to seroprevalence so that we have a data that we could tie activities and the land use analysis to predict to basically estimate the risk zones in certain areas. However, we have only done it for rural areas. So in the context of urban area, we're looking into that, but it requires other tools. So for example, in rural area, we're looking at the use for plantations and forests. So to be able to differentiate, a rubber tree and a palm oil tree is basically different from how you want to differentiate urban areas in high-rise buildings and pockets of a potential flooding area. So this strategy, you can basically look into, if you have the budget and also a wide access to a network of professionals looking into land survey, if you can get those data from them to run a drone with a sensor for heat signatures, that would be very useful for you to predict where would be hotspots for mosquito-borne diseases. Thank you.
Thank you, Dr. Lee. And do we still have another question from participants? Yeah, I think the question is to Dr. Henry first. Questions from Isan Doyo. Malaria medication is only available in endemic area. However, migration occurred. So what will be the solution for this from disease surveillance perspective?
Yeah, thank you very much. Which is actually a really interesting question. We have actually briefly discussed this point together with the National Malaria Control Program in our piece of commentary in Nature Communication, where basically the control program has already established a program where they will provide what they call as malaria kits. Malaria kits. So for those people, those identified as a high-risk population, for example, those forest workers, miners going to the forest and so on, including pregnant women, they will be provided with what they call as malaria kits, which includes certain which includes things like bed nets, for examples. And I think currently there is also a program aiming at the what they call as mobile migrant population, which already include those high-risk population, where the control program is trying to do pre-exposure prophylaxis in the EKN setting. And in terms of what happened if the malaria is happening in non-endemic setting, I think we do have a function of cross-notification, especially if the case is happening in, say, province, for example. I think the logistics is going to be a bit easier because they can then ask for for the available medication, for example, in their neighboring health facility or neighboring district who happen to still have the what we call as endemic or indigenous cases. I think those kind of management can work best in this kind of setting where we do have pre-malaria settings, and on the other hand, we do have a endemic setting who are still providing malaria care. I think that's from me. Thank you.
Yeah, thank you, Dr. Han. For the last 1 minute, do I still have time for the Q&A? Oh, okay, so I will just to do the time, we will only be able to read the few created questions that already shown in the screen earlier. So for those of you whose question we cannot cover during the last question, we kindly invite our speakers to respond directly in the Q&A session. I think there are still 2 questions for Dr. Wawa and also Dr. Henry. Maybe Dr. Lee, if you want to check the other question from the previous participants. And as we're coming to the end of the session, I'd like to thank our speakers for their thoughtful answer and the audience for the excellent questions. Let me close with a simple phrase from the speakers earlier: become knowledge, knowledge become actions, and actions save life. With that, we conclude session 3. Thank you.